Question 3, I assume you all can read this part about the triangular rod. Part A, using integral calculus, show that the rotational inertia of the rod about its left end is ml squared over 2. So, question 3, part A. For any calculate the rotational inertia using calculus questions, always use the formula I rotational inertia equals the integral r squared dm. So now let's look at the problem. This triangular rod, they want the rotational inertia about this point. Now let's consider just any mass of thickness dx and mass dm. I'll just say dm right here. The amount of rotational inertia that this element contributes will be r squared, or in this case they use x in this notation, x squared, where x is this distance, x squared times dm. Now you want to add up all those little contributions of each element. So what you do is use that equation. In this question they use x, same thing, x squared times dm, where dm, to calculate dm, you use what the problem gives you. They tell you the lambda. So dm is just the linear mass density at a certain point, let's say here, the lambda right here, times the thickness of it, which is the definition of the mass, because lambda times the linear mass density times the length will give you the mass. So dm just equals lambda times dx. So we plug that into here. So then I'll say and then I'll use the lambda that they give. Now I need my limits in the integration. So since I'm using dx, the limits start from 0 right there, and then x goes all the way to L. So 0 to L. Now this is just a math problem now. I'll factor out the constant. And the rotational inertia about the left end does in fact equal ml squared over 2. I assume you all can read this part about the two figures. Part B asks, derive an expression for the rotational inertia I total of the hoop rod system about the center of the hoop. Express your answer in terms of ml and physical constants. So I'll just get another sheet. Derive an expression for I total. Alright, I total, using the parallel axis theorem, I see that the question says this hoop has rotational inertia ml squared. So let's just say, sorry, I hoop equals ml squared. They give you that in the problem. 3 rods identical to the rod from part A are now fastened to the thin hoop, as shown in here. So the question above says what each rod has rotational inertia ml squared over 2. So that means using the parallel axis theorem, if I say 3 times the rotational inertia of a rod equals 3 times ml squared over 2, then the parallel axis theorem says the rotational inertia about this point is just the sum of all of these. So I total equals I hoop plus 3 times I rod, which will give us that should be the answer. Part C, I assume you all can read this. Part C, derive an expression for the final angular speed omega of the hoop rod system. Express your answer in terms of m, l, f, and delta t, and physical constants as appropriate. So they tell you a constant force F is exerted tangent to the hoop for time delta t. So when I think about this problem, they say you apply a force like this, and they also say there's a delta t in the problem. I'm gonna think it's an torque equals I times alpha problem. So let me write my net torque equals I times alpha relation. Now, assuming counterclockwise rotation to be positive alpha, the torque exerted by that force equals force times lever arm, force times L, equals I times alpha. Now, force times L, the I, I'll substitute this in for the total I of this figure. And then alpha is just change in angular velocity over change in time. So instead of alpha, I'll write omega final, or just omega, minus omega naught, all over delta t. This is the same. This alpha and this term is the same. The initial omega is 0 because the problem says the hoop rod system is initially at rest. So now I can just solve for omega. Omega equals this term right here, and I can just leave it like that if I'd like. I assume you all can read this. Part D asks, on the figure of the hoop rod system below, draw and label the forces that act on the system. Each force must be represented by a distinct arrow starting at and pointing away from the point at which the force is exerted on the system. Well, we know there's an mg right there, mg, and then there's a normal force exerted on the system from the table. So write F sub n, and then there's a force of friction that's causing the system to not roll or to not slip on the ramp. Since the system is rolling like this, but it's slowing down, the net torque on it must be causing the system to rotate the other way. So I'd say the force of friction is actually up the ramp. Force of friction. Yeah. Yeah, because the other two components don't cause a torque. And if I had a pencil, I would redraw this normal force so that it passes through the center of mass to show that it doesn't create a torque. But anyway, yeah, these normal force, mg, and force of friction. Here, let me... There's mg. There's this normal force. There we go. And then there's a force of friction. This is how I would draw it. Justify your choice for the direction of each of the forces drawn in part I. Well, I would just restate everything I just said. For mg is always down towards the center of Earth, center of mass of Earth. The normal force is perpendicular to the surface the system is on, and is up, not down. And then the force of friction is in this direction and not the opposite one, because the system is slowing down as it's going up the ramp. So that means the net torque on it must be causing the system to be going in to be headed towards a counterclockwise direction, if that makes sense. If the force of friction was the other direction, the system, or this little ramp, this little hoop would be going faster and faster. Part E. Derive an expression for the change in height of the center of the hoop from the moment it reaches the bottom of the ramp until the moment it reaches its maximum height. Express your answer in terms of ml, I total, blah blah blah. Alright, so let's see this. This looks like a conservation of energy problem, since no slippage occurs, so only conservative forces do work on the system. So conservation of energy says U initial, put gravitational, plus K initial for translational kinetic energy, plus K initial rotational will equal U final plus K final plus K final rotational. Now, whenever the system, or that hoop, is at the very top of the ramp, it rolls to the very top, the hoop is at a momentary rest. So there's no kinetic energy, or there's no final kinetic energy at the very top. So now, if we denote U grav equals 0 and H equals 0 at this starting point, then we can say, we can disregard this term, and we can just say the initial translational kinetic energy of this hoop times m of the system, 1/2 m v squared, plus the rotational kinetic energy is 1/2 I total times omega squared equals m of the system times g times the final height. We found earlier that the total m was, let me check. It says earlier that each rod has mass m, and this thin hoop has a mass m. So when this thing is rolling, or this thing has a total mass of 4m, because there are 3 rods and 1 hoop. So the m of the system is just 4m. I'm gonna replace all the m systems. And also v, well, since there's no slippage occurring, the velocity that the center of mass is traveling is just omega times r, and where r is the radius of the hoop, and in this context it's L, so omega times L. So v is instead just omega times L, and then you square that velocity, plus 1/2 I total omega squared equals 4m GH. So derive an expression for the change in height. I'm not sure if they want you to actually solve for h, or if you can just leave it like this, but I'll just solve for h. Let's see. For mgh, I'll flip the equation. Equals 2m omega squared L squared plus I think I'll just leave it like that. And there you have it.